Hey guys, in today's video, we have a call with Steven, a software engineer from Windsurf. In this mock coding interview, we'll go through the entire unfiltered process of figuring out a problem, going through to write the code, and finally validating it with tests. With that intro out of the way, enjoy the video.
Let's go ahead and get started with the question. Let me just post this into the share.
Sure.
All right. Are you able to see this?
Yep. Let me just put this in the comments.
Sounds good.
Okay. Let me just read this. A gene string can be represented by an 8-character long string with choices from A, C, G, T. Suppose we need to investigate a mutation from a gene string start gene to a gene. A mutation is defined. I see. So just making sure that I understand this question properly, what we're doing here is we have a start string, we have an end string, and then we need to figure out, oh, I missed this part about the bank. I was going to say it seems like we need to figure out the minimum number of mutations to, get to the end state, but you don't have an unlimited number of mutations you can make. The big thing is that you have a bank. I'm not sure I fully understand the bank. So the bank defines all of the in-between transitions. Is that what it is?
Yeah, exactly. So you will need to check the bank to see if a mutation is valid.
I see. Interesting. Okay, so normally I think there's some other similar questions where, you can look at something called the edit distance between two different strings, which shows you the number of, modifications you need to make. But the difference with this question is that all state transitions have to go through this bank. So let's see, I only have these 4 characters, A, C, G, T. Making sure this, if I have this start gene, oh, crud. Okay, let me not use Vim mode actually. If I have this start mode, and let's say this end mode was basically the same, except there was a C here, my bank would it be empty here, or would it need to have, the end state in it? That's like a part that's a bit confusing to me.
Right. So it would need to have the end state in it.
Got it. Okay.
Because so that is considered a gene mutation as well, right?
Got it. Oh, this is that's basically the first example where it's just showing a single mutation, but the bank is including the end state.
Yep, that's right.
Let's think about maybe all of the different solution approaches we can use to tackle this. So normally, whenever I think of these kinds of problems, they're dynamic programming types. But because of this bank, that makes me think that there should be some way to maybe connect all of the words together and then try to do, some sort of traversal from a start point to an end point, right? Because the big thing that the bank does is it's basically making some graph formation between the characters. So let's say in our graph you had each of the nodes as one of the words, right? Where start gene is 1, end gene is 1, and then bank is all of the nodes in between. What you would kind of want to do is figure out the edges you need to take to go from your start gene to your end gene. But then the question becomes, what are the edges, right? If that is the graph. I'm thinking you should be able to make edges to, I was going to say the characters, but no, that doesn't make a lot of sense because the position for the words, for the characters is also important, right?
Yes, the position of the letter matters.
So I think if the position of the letter matters, this could kind of be broken up into two different steps, right? When I think of returning the minimum number of mutations needed to go from start to end gene, that means that you're doing something like performing breadth first search, on some already constructed graph, which would give you the minimum number because it's the lowest number of edge traversals you can do. But then now to create that graph, that's, I think, maybe the complexity of the question, right? And what I'm thinking is you would have, let's say you would have your start gene, right, as where you would start from in the graph, and then you would decide to go through the entire bank and then maybe check each of the words letter by letter, if their characters are one-off, right? And if it is one-off, then you know that you have an edge. Does that make sense so far?
Yeah, that makes sense.
This sounds like really expensive to do. I think that's the only weird part here for me. Yeah, so I think we've come up with a solution at a high level, but we have this one big subproblem that we kind of need to optimize, which is how do I figure out, given a string and given the bank, all of the one character edits? And is that even required, right? Let me just put this all down into my idea section. What we're saying is we would originally thought of DP, but because of the bank, that kind of makes that not possible. Alternative thought is each of the genes are nodes and can have edges. If S on the start gene to end gene gives us shortest number of mutations needed. Big Q on how to optimize is how do we find the one care edits fast? And then let me kind of think about the complexity, right? On maybe it's not even required to make this really fast. So if we have a given start gene, is there any kind of constraints on how big these genes can get? Like, are they only going to be, let's say, 10 characters max, or can they get really high?
Yeah, so the question does state that it's all going to be 8 characters.
Oh, does it really? Did I miss that part? Where is that?
Just the first line.
Yeah. Okay. I actually completely missed that. Okay, so if that's the case, then, this whole single letter by letter comparison, we don't even have to care about it, right? Because that's just constant time now. So constraints, we can say all genes are 8 characters max. And I guess the only reason we would even bother with this graph traversal option is because even if you only have 8 characters, I'm pretty sure that's still like a commentarily huge, number of possible genes you can have, right? Because it should be what, 4 to the, wait, that's not even that big. It's what, 4 to the 8? Sorry, I'm just gonna do that real fast. Oops. Yeah, it's actually a tiny amount of possible start and end genes and banks that we can have. So then I guess my question to you here is, this graph approach to me makes sense, but is it really even required? given
Well,
that there's almost no, real complexity issues
yeah,
in terms of runtime.
if your question is if the graph traversal is required, honestly, it's just whatever method helps you get to the answer, right?
I see. Okay, got it. I think the graph traversal method still kind of makes sense. High level.
Mm-hmm.
So maybe we will just go with that.
Yeah, the graph traversal sounds like a sound implementation.
Okay, let me just, before we code it out, word out some of the complexity here. In reality, because of what we said, I think this counts as basically O of 1, right? Because the n is super, super constrained here. Because I think no matter what, you can't have above the 4 to the 8 possible different genes, right? If they're limited to 8 characters.
Mm-hmm.
Yeah. Finding. Cool. Then if that all sounds good to you, I'll go ahead and code this out.
Okay.
Sure.
Yeah, that sounds good.
Num mutations, which is going to take a start gene, and then bank. Let me just move this up. Okay, so what did we say we were going to do? Right. So we said we have a graph. We're going to perform BFS. We are going to start with the... This is wrong. We're going to start with start node and then move outwards, right? So collections, import DQ, num in mutations, set 0, which we're going to return. Q is going to just be an empty queue to start, and then we can append our start gene. Let me think about this actually, what we would actually be putting into our queue. So because we're trying to figure out the number of full level traversals in the queue, we not only need our gene, but we also kind of need the an initial level. And so that's so that as we go through, we can figure out, not the number of total items that went into the queue, but instead the distance, right, between the start and end. So we have our queue, gene level. Oh, no. For each item in the queue, what we're going to do is have the gene and the core of the problem becomes, how do I make sure, how do I actually find all of the items inside of the bank that are just one level different, one character different. Even though I said it's really simple to do this, I still think there's like a couple of different options, right, on how you do the one character difference. So one option is that you could try and change every character to one character different and then see if that exists in a set for the bank. That sounds kind of not great. maybe the other option is that you go through the bank and then you do just that direct, comparison there, right? To your existing gene, and for each character in the bank, if it passes, then you go ahead and include that as one of the neighbors.
Mm-hmm.
I think I'll go with the second because it's probably simpler to see as code. And then again, we said we don't really care that much about the performance of this operation, right?
Okay.
Yep. So def single diff start end. Found diff is going to be false. What's going on with the spacing here? Okay, so all this function is doing, just to give like a quick explanation, you're taking, some start gene, you have some end gene, we're looking for a single difference between them. We can just say that originally there is no difference. We're just going to go through each of the characters letter by letter. And the first time we find that there's a difference, we just record that, okay, we found one. But the second time we find a difference, we know that now there's more than a single difference, right? So we can just return false, and yeah.
All right.
We can use this function to now go through all of the items in the bank. With the only thing that maybe we don't do is, we don't want to repeat visit elements, right? So, but I can come back to that. Yeah, so what we want to do here is for gene in bank, if single diff between transition gene in bank, if single diff between gene transition gene, then q.append transition gene with level +1. Right. And so I believe this is, the core logic of what we wanted to do, with the only real thing that we need to also include is for BFS to properly work, we need some visited set, right? To make sure that we're not revisiting nodes. Oh. Not be the second condition. If transition gene not in visited, I messed up something here really, really badly. I don't actually have logic that is taking us to our end gene. Yeah, I messed up here. Let me think if I just need to break if I find the end gene, or if something else needs to be done here. Okay, so starting off, what we did, we have our function mutations start end gene with the bank. We start off with min mutation 0. We have our queue. We append the initial gene to the queue, and we have visited to properly run BFS. Okay, what we're going to do is we're going to do a level by level traversal to count the number of mutations required. by just counting the number of items in the queue, and then for each of them, trying to do a one-level shift to something else using single diff. And then I guess the final thing is if gene is equal to n-gene, we can break early. And is there a return condition for... Oh, okay, it says over here you always have... okay, you return -1 if there is no n-gene that we find. So over here, what we'd actually return is not break. We would just return min mutations. And then over here, we'd return -1. Yeah, I think that's probably it for the problem. Is it okay if I go ahead and test this out?
Yeah, sure. We can do that.
Okay, let me do it with... let me do it with this one. Oh, that did not copy. Does it say what the output of this is supposed to be? Oh wait, I just realized the examples don't even have... Example 1 doesn't even have what the output is.
The output is 1. Yeah.
Oh, okay. I didn't see the colon here. I read that as output 1. Thank you.
Yeah.
Okay. Anyways, let's go through and see what happens here. So our queue is going to start off as just the start gene. So we have our visited set as just the start scene as well. We're on level 0. We are going to go ahead and look at the number of items, which is going to be 1. And then so for each of the number of items, we decide to pop off. So we'll have this gene set in. If the gene is an n gene, we check it's not. So we check for each transition gene in the bank. We just find 1. So this transition gene is not visited. And, you know, I'm not going to check letter by letter here because I guess we already know that there's a single letter difference. We'll find that the single diff passes. So we're going to add it to visited and then append this to the queue. Okay, the number of min mutations goes to 1. We're now at the next level. We pop off. We see that this is the n gene. Our min mutations is 1. And so we'll return 1 as we expect. Let's do input 2, which I think might be more interesting. Let's see. What is the actual path taken here? I mean, it does display it, right? Oh, sorry. What is this part on line 24 to 27?
24 to 27. Yeah, so that is, I believe that's what you wrote.
Oh, sorry. Yeah, I thought that was part of the examples again.
All good.
I kind of blanked on that. Right, so let's go through our example 2. We start off with this AACG-GTT, and we'll have the same thing. There's a single item. We know that it's not the n gene. Let's look at all the transition genes in the bank. We look at the first one. It's hard to tell if these are a single edit or not from looking at them. I believe this one is, right?
You can put it next to each other to see if you'd like, but yeah, that should be just one letter apart.
Are they all one letter apart? They almost look like they're all one letter apart. Oh, wait. Are these not? These are all the exact same. Oh, no, they're not. This one has an A. This one has a G. Yeah, this is like actually really hard to see as a human, I gotta say. Hmm.
Yeah, so 1 and 3 are 1 letters apart. 1 and 2 are 1 letters apart.
1 and 3. What are you referring to as 1 and 3 here?
So 94 and 96 are 1 letter apart. 94 and 95 are also 1 letter apart.
I see. Okay, maybe going through this thing line by line isn't the way to actually test this, but we can try and just like reason about it, right? The same way as we did, for example, 1, and maybe that's to kind of check if some kind of conditions are always true in each iteration of our loop, right? And so the conditions that are relevant is that at the start of the loop, you should always have the current frontier of single genes that we want to look at, right? And from our previous example, we could see that that's definitely, I think that's going to be true. And then the thing we care about is in between, are we making sure that we're not revisiting items so that the frontier doesn't go backwards? And I think we do cover that. And then are we counting correctly? And then we do kind of cover that. So then I think instead of going through this line by line as an example, I might want to think of some other example test cases which might be bad input or something like that. So let me just go ahead and relook at the initial question and see if there was anything about, yeah, okay. The starting point is assumed to be valid, so it might not be included in the bank. We can always assume that the bank is always valid characters and everything as well, right?
Yeah.
Got it.
They'll all be valid strings in the bank.
Sure. I guess given all of this, I'm just going to say that this is my... okay, let's actually look at single diff again. Yeah, I think this checks out. I think I'm going to go ahead and say that this is my final solution.
Okay, sounds good. Yeah. So then I think like from here, where would you like improve if you had more time on the solution?
Where would I improve? I mean, the main thing we care about here is kind of the correctness, right? And right. So I think in terms of code quality, we're probably, we're fine, right? As it is. I don't think a function like this, you want to make it more complicated. Yeah.
Okay. So no improvements.
Yeah, I think in terms of overall structure, like I would be satisfied with these functions in isolation.
Okay. Yeah, that sounds good. So then, yeah, like let's just end the mock interview here, right? We can maybe take a bit of time to just kind of see how we did. What is your kind of like self feedback on this interview?
Sure. Okay. Yeah, I guess we can start with the. Oh, did you want to start with my self review?
Yeah, we can just start there and then see if there's anything else.
Yeah, I think in terms of figuring out a solution approach, so I can talk about the things that went well. I think the initial part where we're going through the ideas and the constraints, that went decently well because, we're talking through the constraints of the problem, any assumptions we might have, making sure we understand, the problem, as well as talking about, what we actually have as time complexity and things like that, right?
Okay.
And whether we need to improve on the solution that we came to, using the complexity as the basis for it. I think those parts went well. Again, I'm kind of assuming this code has no bugs in it, almost, because it, from my point of view, this looks fine. So if this was, bug-free code, that would be a huge positive. But the thing that might have knock on well here is that I think I was a bit all over the place with the code itself. I think I felt a bit unfamiliar with writing out the code just because it's been a while. Yeah.
Okay.
And the testing is not great. But I feel like this question is a bit harder to test than a lot of other questions because when I'm looking at these strings, they all look the exact same to me.
Yeah. Yeah. It's a bit confusing to like go through in person for sure.
Yeah.
But yeah, I think agreed. I think it's just like you sort of like my comments on this was that, yeah, I think like the assessment was correct. I think you understood the question well.
Mm-hmm.
What was interesting was like you were thinking about like kind of one tree based approach and then flip flopping sort of between a couple of approaches. And so I think like that was really just a matter of committing to one. I think that would have been interesting to see like the tree based approach. But it seems like when you actually did implement it, you went with just like a queue based approach, right?
Wait, what do you mean here by a tree-based approach?
Yeah, so like I think that essentially, well, yeah, I guess like for me, what I was thinking about when you were describing like a tree is maybe building like a state tree from the bank, right?
Right.
That could have been possible as well. So I thought it was leaning towards there. But
okay. Yeah, I guess I didn't explain that fully, but yeah, the initial thing that I was talking about was making the tree and then doing the separate BFS. But then what you realize is that you can just run the BFS and implicitly this is a graph, right, that you're traversing. But you don't actually need to construct the nodes.
Yeah.
But this is basically like a graph traversal, right? That you're running between the actual genes.
Right. Yeah. So I think like that, I think was just like the one piece that I felt was a bit confusing for me, at least. Right. But
because I said one thing and I didn't exactly do something different, but I did something different because it's kind of, I didn't make the graph I said I would. It's like implicitly in there.
Yeah, but overall, like I think it was still strong, and you ended up with a solution that did work. I think like just a minor thing about improvements was like, yeah, I guess there's an opportunity since I know we talked about not worrying too much about compute, but what I would say is like the single diff being called repeatedly is an area where we could like have micro improvements, right, in terms of improving the computation time of this algorithm.
Let me actually think about that. We did kind of like go straight into just writing it like this, but I'm now that we have like maybe less of a rush to go out and find a solution, let me think on if you actually would improve this somehow. I think this is given the structure I used here, this is definitely going to be the fastest way to find the single diff.
Yeah, I think it's more so like I think repeatedly calling it on the remaining nodes in the bank, right?
Oh, so you're not. I get what you're getting to.
Yeah.
That we're repeatedly going into this for transition gene in bank. Yeah, the improvement that we could do here is that instead of making the bank a list, you could make it a set and remove items from the set, right? Which would kind of double as the visited.
Right.
But we don't run single diff because if we visited, then we just skip, right? But I get what you mean.
Yeah, man, this is a micro improvement, but I would say you still like. I think the way that this question is designed on LeetCode is meant to be sort of like brute forced, right?
Mm-hmm.
So because of like one constraint that I think you didn't, or I don't know if you saw it, but like the bank length is also limited to 10.
Wait, is that really part of this?
So the last part where it says the constraint.
Oh,
Yeah.
I actually didn't even see this constraints parts. That's actually pretty
Yeah.
bad.
All good. Yeah. I would say like just like when something's like kind of constrained out like that, I think just going just brute force does tend to work quite well, right?
Right.
So that would be like the one thing I would call out. But overall, like I think the reason it was strong, you ended up with a solution and you tested out. So it was all good there.
Cool.
Yeah.
Awesome. Yeah. Thank you for your time.
Yes, sir.
Yes, sir. God damn.